So, so I posted the last lab assignment. So it's a lab 6. And then in this lab assignment, you were requested to design pipeline the processor. Okay. So, and then actually, so I provide the, the RTI model. So it means the system verilog file of the single cycle processor design. So actually you can start from this single cycle processor design. Okay. So, and then actually people starting, uh, people explaining about the, the lab assignment, the lab 6 assignment. So I will explain about the simulation tools. Okay. And then I will explain about the lab assignment. And then, so we will discuss about the memory hierarchy. Okay, so let's discuss about the simulation tool in computer architecture research. So, so so actually I showed this figure in the first class of the this course, right? So so computer system is composed of the many layers, okay? And then we learned that we just focus on a certain layer for our study, okay? And then I explained that we are learning about the microarchitecture and architecture level, okay? So and then so and then we also learned about the abstraction. So abstraction means that we just focus on the required knowledge, and then actually for other layers like the logic layer, analog circuit, and then blah blah blah. For other layers, if the knowledge is not required, so we do not focus on this knowledge, right? So this is the concept of abstract. So in this course, so we are focusing on the architecture and the microarchitecture level abstractions, right? So we are focusing on the instruction set architectures, that is kind of architecture level. Also, we learned about the, the CPU design or CPU architecture, and then actually it's called microarchitecture. So architecture of CPU. So we learned how to design CPU hardware. So it means we were focused on the microarchitecture level, computer system. Then for research, how can we do our research on computer architecture area? So think about so not this one. Okay, so so the in this course we are focusing on computer system. Actually, we are focusing on the hardware of our computer system and software hardware interface, right? So we are focusing on software hardware interface. Then how can we implement our idea? So think about the processor design. So so in lab 5, so you are requested to design the single cycle processor, right? So what did you use? You used system verilog, right? So in order to design the single cycle processor, you used the system verilog, that is the hardware description language. So actually, it's not real hardware, right? So we are working on the hardware, uh, hardware research or hardware study, but we use a programming language, right? It's a software. Actually, so you designed behavioral model. So what does that mean? Actually, so in order to build a CPU chip, so actually we require to know about some circuit, the knowledge on the circuit design actually. So it's just implementation. In order to implement, so actually we require this knowledge, like the analog circuit design, device design also. So we may need to know about the the electric physics, right? So the starting point is the kind of the movement of electrons, and then also we need to know about some characteristics of the semiconductor materials, blah 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 blah. But for this study, so in this course, the computer architecture course, we did not learn about this knowledge, right? So and then you don't need to know actually, right? So we just describe the behavioral model of the CPU. Okay, so it's not real hardware, right? So think about your program, right? So your program, so you need to write a code to make the application, but this is not a real. Um, Actually, your code just describes the behavior, like the A plus B and C equal A plus B, or T equal B plus 1, blah, blah, blah. So actually your program just describes behavior of your application. It's not a real it's not a real thing. So real thing is the compiled machine code, right? So compiled machine code run on the CPU, right? It's the same, the hardware design. So we made a behavioral model of our CPU. So this is not a real hardware. This is not real hardware, but using this model, we can emulate. Okay, so what is what is emulating? What is the meaning of emulation? So we can it's emulation means that it's not a real thing, but we just mimic. We we can mimic. So it means we can just it's the same meaning actually, right? So well, it's not a real thing, but we just describe some model. It's a model. Okay, it's just kind of abstraction, right? So using this model, then we can work on the computer architecture research, right? So actually for our research, so you can you can observe this board. So we we may use, so we may work with the real hardware like this. So it looks very complex, and then it's true, right? Actually, it's not easy to use this board. So unlike the software debugging, the hardware debugging is so difficult, right? So the software debugging actually it's very convenient, right? We can just trace the exception points, and then we can just check the why exception why this exception uh, happens in our program, right? And then also we have very convenient debugging tools. But hardware is the real thing, right? And then also the hardware, the actually not to run the hardware, and then we need to provide the electric power, which means actually the electric signals communicates in the in the hardware, right? So actually in order to debug the hardware design, we may need to check the the electric signal in this board on this board, right? So it's not easy actually. So actually for this architecture research, so we can use the simulator. Okay. So actually, as I mentioned, we can work on the real hardware or real computer system. So it can be possible, but usually we use simulators. So simulator is a software, right? It's a software, and then simulators emulate, right? So I said mimic, okay? Mimic. So simulator is a software that can emulate the behavior of the hardware. It's a simulator, okay? So think about the spike simulator. So in the lab, lab number 1 and number 2. So we used Spike Simulator. So it's a software, right? It's a totally software, right? And then we don't have the RISC-V CPU, but we can run RISC-V instructions like on real CPU, right? So if you run the Spike Simulator, then you can check how the registers are changed. Also, you can check the 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 data in the memory, and then how the memory contents are changed in the Spike simulator, right? But it's a software. It's just a software. Even though we can run our binary file, the RISC-V binary file, but it just emulate. It just uh, emulate the behavior of the RISC-V CPU. So it's a software. So we can just use the simulators for our research, the computer architecture research. So, and then, the RISC-V is the open source ISAR. So actually, many simulators are developed, well, many simulators have been developed by the academia labs, okay? So there are many open source simulators for RISC-V. So it's a very good thing. It's the advantage of the RISC-V research because we can use open source simulators. So you think about ARM. So ARM. So in order to use, in order to develop the ARM, not ARM hardware, in order to develop the ARM-based system, then actually we need to use the very complex the IDE, but this IDE was developed by ARM, and then actually we need to purchase, okay? And then actually we don't know the inside of this ARM simulator, right? Well, ARM development environment, okay? But actually for RISC-V, because RISC-V is the open source ISR, so the many academia labs have developed the simulators, right? Like the Spike. Spike is also the open source RISC-V ISA simulator. So you can find the source code of Spike in the GitHub, right? So anyway, so there are many simulators for RISC-V, like the assembly simulator, like Spike, right? So assembly simulators can run RISC-V assembly code, right? So you can also virtualize the RISC-V environment using QEMU, okay? Like a QEMU, okay? So it means even though we don't have the RISC-V hardware, that we can run RISC-V binary code using these assembly simulators. Also, we can check some content in the register file, also content in main memory using this simulator. So there are, so if you are interested, you can visit the homepage for these simulators, okay, and you can run, okay. So also the RISC-V has the graphical architecture simulator, right? So RIPES is a RIPE, okay, not RIPES, okay. Oh, it's a RIPES, right? It's RIPES, okay. So so also you can download RIPES from GitHub, okay. You can run RIPES on your Windows machine or Mac machine, okay. And then actually this is the graphical simulator. So which means, so we can configure the RISC-V CPU using the single cycle model or 5-stage pipeline architecture of the RISC-V like this. So good is that, so using this graphical simulator, so we can observe how instructions are executed in each stage of risk 5, we can check, we can observe how instructions are executed in each stage, right? So in this example, you can find several instructions, right? Here, okay? And then, so you can also observe the content in the register file, and then also uh, you can observe the pipeline stores and data forwarding. Actually, in this using this graphical simulator was RIPES. So I think it's a very good application, a good simulator. Uh, but our problem is that so this is the open source simulator, so it's not maintained well. So the open source applications are not maintained well, right? It's just free, right? So sometimes these simulators include bugs. Okay, also I know the bugs of the RIPES simulator. Okay, so so actually, so in the lab 6 assignment, so you are requested to design the pipeline architecture, right? Then you can verify. You can verify your design using RIPES. But so as I mentioned, the RIPES has a bug. So sometimes it's not. It does not generate the incorrect result, but the timing can be incorrect. Okay, so you can find the bug. So actually, if you uh, so I provide the binary code. Okay, so the instruction memory is the loaded with the this binary code, right? And then this binary code actually includes an instruction that caused a bug in this RIPE simulator. Okay, so you can check the bug using the provide uh, the binary code, and then I don't think uh, the bug is fixed. Actually, I don't think so. Anyway, but so using this simulator, so this is a very good tool. Okay, so so as I mentioned, the pipelining, the concept of a pipelining is it's very easy, but uh, some concept like the hazard detection, data forwarding, also the control hazard. So in order to implement these mechanisms, actually it's not easy. So it may be tricky because we need to consider the real behavior of the hardware. Okay, so we are very familiar with the software coding, and then as I mentioned, the software coding is very easy, right? And they're very convenient. Okay, it's a very easy, right? But actually, the software, in the hardware structure is more complex, and then in order to handle some exceptional cases or the boundary cases such as the data hazard, the control hazard, and then also the data forwarding, we may require more complex mechanisms in the hardware. Okay, so that's why the hardware, uh, the architecture research, so, so usually it's more difficult, but it's fun. Okay, so compared to the software research, it's fun. Okay, okay. So and then using simulator, then we can also perform the research on this hardware, the architecture research. Okay, so put the the lab assignment number 6. You can also utilize the architecture simulator. Okay, you can. So by doing this, you can understand how instructions are really executed in the hardware, the complex, the 5-stage pipeline architecture. Okay. So then I will briefly explain about the lab 6. Okay. So this is the last lab. Okay. And then unfortunately the lab deadline is so June 10, right? So it's June 10 is before the final exam, right? Okay. Okay, so the 5-stage pipeline architecture. So you need to design the five-stage pipeline architecture, right? So and then actually you can start from the single cycle processor design as I mentioned, right? So and then I provide the the RTL code, the system verilog file for the single cycle processor design. Okay, so it means this is the okay, this is the golden version of the lab 5, right? Okay, it's the so it's a some final it's a final it's the uh, answer. Okay, so it's a golden version of the lab 5 will be it was provided in the lab 6 assignment. Okay, so you can find the single cycle CPU.sv that includes the golden version of the lab 5. Okay, so anyway, so if you fail to complete the lab 5, but you can start lab 6. Okay, so you can start the lab 6 from the single cycle processor design, the provider single cycle processor design. So anyway, so how can you start? How can you start the design of the 5-stage pipeline architecture? So from the single cycle processor design, we can just split the single cycle processor into 5 stages. So 5 different stages to the instruction fetch, instruction decoding, execution, memory, and write back. And then in order to build the 5-stage pipeline architecture, then we can just add the pipeline registers, right? Like this. So these pipeline registers just sample the signals from the previous stage using clock signal. So I said these pipeline registers are D flip-flops, right? So this is because what is the definition of a register? A register is a group of D flip-flops actually, right? So we can just insert pipeline registers in the single cycle processor design, right? Like this. And then the signals are sampled by these pipeline registers, right? Then so so I will explain this later. Then let's see how to design the pipeline register. So if you read the lab 6 skeleton code, okay, so like the lab 5, I provide the skeleton code of the pipeline CPU, and then in the code you can find some new structure. Okay, it's like you can find some data type like this, like a type defeat. The type is defined, and then there is a structure type, right? And then it's a packed. So it's called the packed structure. Okay, and then this is the feature or number of features of system Verilog. And then actually this packed structure is similar to structure in C. Okay, so what is the structure? What is the structure in C? So we can group multiple variables, right? And then we can define new variable type, right? Using the structure in C or C++, right? It's the same. It's the same to the system Verilog. System Verilog provides the packed structure. It means the multiple variables. In system Verilog, we just use large variables, right? Like this. So we can just group multiple variables in one data type, one structure type. Okay. So if you see this type, so I just name this structure type as the pipe underbar if underbar id. So what does that mean? It means it is the data type for instruction fetch slash id pipeline register, right? And then in this type, in this structure, there are multiple variables, right? So you can find the PC and instruction. So what does that mean? So if you see the instruction fetch slash ID pipeline register, then this pipeline register samples, this is the PC, this is the instruction. And then this is sampled by clock, right? So using the packed structure, and then this structure name is pipe underbar instruction fetch underbar ID. And then using this structure, I group the multiple variables, PC and instruction. So, so, and then also the width of the PC is 32-bit, and then the width of the instruction is also 32-bit, right? And then I declare this pipeline register name is ID. So why? So this is the D input, and then this is the Q output of the pipeline register. This is the D flip-flop, right? And actually, in the ID stage, so in the next stage, we use these variables, right? So if the program counter is sampled by this D flip-flop, like pipeline register, then we will use this sampled output in the ID stage. So this output, the Q. So this output is the signals utilized in the ID stage. So that's why I named this variable name is ID. Then we can use these signals like ID dot PC or ID dot inst. Okay, so we can use the signals like this. Okay, so I also show the example, another example. So example like here. So actually, this is the complete code for the instruction fetch slash ID pipeline register. Okay, so what can you observe? Okay, so ID is declared here, and then as we use the ID, the type of the ID as we define the type of ID as the pipe underbar instruction fetch if underbar ID, right? And so also you can find the comment here. So, and then we just define the behavior of this pipeline register. So, this is the D flip-flop, but we need to add the control signals for this pipeline register, right? Because we need to control pipeline store Also, we need to control flush. Okay. So if you read this code, okay, so it just defines the behavior of the pipeline register. So for the reset case, so if so, you know this is the underbar B, so it means it's the negative reset. So which means if the reset underbar B is 0, so which means it's reset, right? So all signals become 0, right? And then this is the reset state. And then it's a for the normal operation state. So for normal operation state is defined here, right? And if you see this one, then if flushy, the instruction fetch underbar flushy is activated. So if this is 1, then all signal output becomes 0, right? It's flushy. So it just generates the bubble, but it makes all output like PC id.pc, and then this is the id.inst. So these variables become 0, means nope. And then if, so you know, it means not instruction fetch underbar store. So what does that mean? So instruction fetch is not stored, right? Because this means the not, this is the not in system value. Okay, so what does that mean? This is the normal operation. So the store is 0. If instruction fetch underbar store, it means, so if this signal is 1, it means the instruction fetch stage is stored. But I just mentioned, use the not signal, which means if this signal is 1, right? Because we just use the digital signal, right? Then you can find the id.pc is the PC core, and then id.inst is the inst. So this is the PC underbar core, current PC, and then this is the instruction from the instruction memory. So what does that mean? On the rising edge of the clock, so you can find the positive edge of clock. On the rising edge of the clock, then this id.pc is updated by PC underbar core, and then id.inst is also updated by inst. Okay, it's a sampled. So it means these signals are propagated to the next stage. Okay, so when we learned about the pipeline architecture, I frequently mentioned that, oh, this instruction was in the some stage, and then this instruction is propagated to the next stage on the rising edge of the clock. So this just to describe this signal propagation, the behavior of signal propagation to the next stage. Do you understand? So, and then in the id stage, we use these signals. So that's why I named this pipeline register as ID. So which means if you just see this name, then you can figure out, oh, these signals will be utilized in the ID stage. That right? Because this is ID.pc. Okay. So if you read the skeleton code, of the lab 6, then you can just find the signal, the name convention like this. Okay. So name convention is also important for coding, right? So because actually the most bugs are, so actually the human makes bugs in our code, but actually the bugs are caused by the misunderstanding or some uh mistake, right? So you can think this is the mistake, but it's a misunderstanding, right? So that's why. So we just actually in the skeleton code, so you can find some name conventions like this, and then try to understand these name conventions, right? Then you actually, so if you make a bug, then actually the debugging is tricky, right? So it takes a long time actually, right? So we need to reduce the mistakes or misunderstanding in writing a code, right? In writing code, right? So try to understand the name convention in the skeleton code, okay? So this is the normal operation. Then you may think that, oh, the pipeline store is not defined, right? But actually the pipeline store is defined. How? So what is the pipeline store? Okay, its pipeline is stored, then does this output. Actually, this output of deep flip-flop is not updated by this signal. It's maintained, right? And then in the deep flip-flop design, if the output is maintained, then we don't need to define the maintained signal. Do you understand? So, I define the behavior of the pipeline store. No, pipe flush operation here. And then this is the normal operation of the pipeline register, right? But I do not define the pipeline store in this case, because what is the pipeline store case? If the instruction fetch underbar store is 1, then it's pipeline store case, right? But if the pipeline is stalled, then the output. These signals are just maintained. So we don't need to define the change of signal values in the D flip-flop. It's because this is the always on the FF. So it just define the flip-flop, the behavior of flip-flop synchronized by clock signal. But if you just read this behavioral model, and then we just define how the signals are changed on the rising edge of a clock, right? Do you understand? So in this behavioral model, we just define how the signals, which means how the output signals of deep flip-flops are changed when on the rising edge of a clock, right? So I mentioned how changed, but if the signal values are not changed, we don't need to define this case, right? So this is the store case, the pipeline store case. If the pipeline is stored, then the output of these pipeline registers are maintained, right? So we don't need to define the behavior of this case, right? So actually it means the pipeline store is also implemented in this code, okay? I define the behavior of flush, define the behavior of normal case, and then pipeline store just maintained. Okay, it's not defined, but it's implemented. Okay, so actually the first pipeline register, the behavior of this instruction fetch slash ID pipeline register is already defined in the skeleton code. So it's defined here, right? You can design other pipeline registers like this, okay? So signals are given to the pipeline registers, and then on the rising edge of the clock, then the signals are propagated. So which means the outputs of pipeline registers are updated by the input of pipeline registers on the rising edge of the clock. Okay. Okay. And then, so as I mentioned in the class, so actually, so in the textbook, in order to reduce the control hazard, so in the textbook you can find the equality check logic just after the register file. But I mentioned that in order to implement these, we need to define more complex hazard detection, right? So actually for this lab 6, we assume that dedicated branch unit is here, right? So the branch instructions are handled by this branch unit. Okay, so you can find the BU underbar blah blah blah. So it means the branch unit signals. Okay, so the branch is taken, then the penalty is 2 cycles. And the branch is not taken, then no penalty. There is no penalty. Okay, and then lab 6, for lab 6 design, we assume this pipeline, the five-stage pipeline architecture include a dedicated branch unit in EX stage. Okay, in the EX stage. And so then the hazard detection is simpler. Okay, simpler than the textbook version. Okay, so I explain here. Also, when you learned about the data forwarding, so we assume that the internal forwarding is supported by register file, right? So what is the internal forwarding? If the new data is being written back to the register file, this new data, this new data can be forwarded into the output port of a register file. So this is the internal forwarding. So actually, for the single cycle processor design, the register file does not need to support internal forwarding. So, so in the register file design, actually we design the register file in lab 4, right? Lab number 4, right? But for the lab number 6, we need to use the new register file, right? So, and then this new register file needs to support internal forwarding, right? But so actually for this lab assignment, you don't need to design the new register file. So new register file is already provided. And then, but I just show this code because because I want you can understand how the internal forwarding is implemented. Okay. So this is the new code of the RS1D out and RS2D out in the register file. Or actually, this is small d. Okay. So, and then this part defines the internal forwarding behavior, right? So if you read this code, the reg write is a reg write signal, and RS1 is equivalent to RD, right? So this is the RS1 register number, and then this is the RD register number. Then D in is forwarded to the D out, right? So this is the internal forwarding, right? So internal forwarding is already implemented inside of the new register file code, okay? And then, these are the existing code, right? Right? Because the RS, so this existing code, so describe. So if the register number is not zero, then register data is out. Now, if the register number is a zero, then out is the zero because it's always a zero, right? So internal forwarding is already implemented in the register file. Okay. So actually, this is the I think this is the uh, tricky part. Tricky part in this lab assignment: data forwarding and hazard detection, right? So data forwarding. The data forward. So actually, in chapter 4, we learned about the data forwarding. So which means there are the forwarding multiplexers in EX stage, and then based on the forwarding condition, the data are forwarded from the memory stage or write back stage, right? So data can be forwarded like this, and then data can be forwarded from the write back stage. Okay. So you need to implement the data forwarding in the pipeline architecture. So, and then as I mentioned, so this is the tricky part. So I don't think the pipeline register design is I don't think this is difficult, but the data forwarding can be is a little bit tricky. Okay, so which means if you make a mistake for designing this data forwarding, then you need to debug, but the debugging may be difficult. Okay, so you need to design the data forwarding unit and then the forwarding multiplexers in the pipeline architecture. Also, the hazard detection. Okay, and then actually good thing is that the branch unit, that the dedicated branch unit is located after this forwarding mux. So actually we don't need to consider some special cases for data forwarding or branch instructions. And then also we need to define the hazard detection. Okay. So hazard is caused when the former instruction is load instruction, right? So which means we need to detect the load instruction, and then the follow instruction uses the destination of the former instruction. Then we need to detect the hazard, and then also we need to define the behavior, the hazard by branch instructions, right? So you need to implement this one. If the branch is taken, then the instructions in instruction fetch and ID needs to be flushed. This is the control hazard, right? The branch is not taken, no penalty. So we don't need to flush the instructions, but you need to implement this case. It's the hazard detection, okay? So firstly, you need to detect the hazard cases, and then you need to implement the behavior, how the hazard handling, okay? So this is the kind of a tricky part in the lab assignment. Is a lab 6. Okay. So please start early, and even though you have two weeks to book until the deadline of this lab 6, but I recommend you to start early. Okay. Okay. And then if you have any questions, and then you can post your questions on Piachan. Also, you can get help from TAs. Okay. 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 So I explained about the lab 6. And then so we have around the 20 minutes. Then okay. So we will learn about let's learn about the memory hierarchy. So so we learned about the various memory technologies in the previous uh, class. Also, actually, the important thing is where is the memory hierarchy? It's this one, the memory hierarchy. So you need to understand how the the slow memory, how the slow memory is handled in the computer system. And then I explained that the slow memory is handled by the memory hierarchy, right? Like this. And then so you need to understand the characteristics of each level of memory hierarchy. So it means for the high level memory, so this is the high level, this is the low level memory. So for the high level memory, so we use expensive, so it means the good memory, the better memory. So what does that mean? Which means, oh, this memory is fast, but the capacity is low. So I explained that if the memory size is large, then the performance is low. Okay, usually, usually. Anyway, for the high level memory, the capacity is low, but the performance is high. For the low level memory, like the storage or main memory, the capacity is high, but the performance is low. It's slow. So then why do you use memory hierarchy? So we want to use the fast memory, but actually the capacity is low. So we can store frequently used data in the high level memory, right? So by doing this, we can improve the performance of a computer system. Then why? So why can we use memory hierarchy? So it is because our applications exhibit strong data locality. Now, there are two kinds of localities, the temporal locality and spatial locality. So this is very important concept, right? So you need to understand the definition of the temporal locality and spatial locality. So because of this, we can utilize memory hierarchy, right? Because of locality, so we can just store the frequently used data in the high level memory, then we can access these frequently used data quickly with the high performance, right? So this is the idea of memory hierarchy. Also, I explained about the behavior, hit or miss, right? It means, so if we first, the CPU, the processor first access the high level memory, right? First, but it means that because the size is small, it means we cannot find every data, every request data in the high level memory. It can be found, but also it cannot it is it cannot be found. It is not it okay. So if the data is found, this is the hit case, and then if the request data is not found, it means it is the miss case. So we define the hit ratio of the high level memory, like cache. Okay, that's what we learned. So in order to increase the performance, then we need to increase the hit ratio. Obviously, it means the request data are frequently found in the high level memory. Then the performance can be improved. That's what we learned in the previous class. And then we learned about some various memory technologies, okay, like DRAM. So actually, only this part is different, right? So the memory structure, memory structure is composed of word line and then bit lines, and then word line activates the memory cell, and then if the memory cell is activated, we can read or we can write data to from what to in the memory cell, right? And then I explained that only this part is different for the different memory technologies, okay? Like SRAM or DRAM. So only this memory cell, these cells are these cells are different, okay? And then actually the characteristics of these B cells determine the characteristics of memories, right? Right? Okay, so we just compare the characteristics of SRAM and DRAM. And then actually as I mentioned, the DRAM is the behavior of DRAM is very complex. It's more complex than the behavior of SRAM, but I will not explain about this behavior. Okay. So like this. But I hope you can understand this. So I believe some of you have heard about the terminology, the memory bandwidth. So actually we learned about the no. We learned about the throughput, right? So it's a throughput. So what is the throughput? So when we learned about the performance terminology, then we learned about the throughput. Then what is the definition of a throughput? Definition is the amount of work done in unit time, right? So this is the definition of throughput. Bandwidth, the memory bandwidth. Actually, the definition is similar to the throughput. And then bandwidth means it's the amount of data per unit time. So during the unit time, this amount of data is transferred to the CPU. Then we can call this is the bandwidth. Okay. So, and then, like the throughput. So actually, the definition of bandwidth is also similar to the definition of throughput. And then we can use this bandwidth as the performance metric of memory system. So which means if the bandwidth is high, then it means the performance of memory system is also high, right? If the bandwidth is low, then the performance is low. Then how can we increase the bandwidth? So bandwidth, the bandwidth is the amount of data transferring from the memory, right? So which means If the memory is fast, we can increase the bandwidth, obviously, right? So if the memory is fast, then we can increase the bandwidth, right? But what's the problem? The memory is slow, okay? Because the memory is slow, we actually using the one chunk of memory, we cannot increase the bandwidth. Okay, so we want this performance. So you can find, so this is the bus, and then this is the memory, and then actually is we want the memory provides the high bandwidth. But problem is the memory is slow, right? So, and then also in order to provide the high bandwidth, then we need to increase the number of channels. So what is the channel? So channel is so like in the communication, we frequently use the word channels, right? Because then what is the channel? Channel is a media for communication, the data transfer. So using this memory channel, the data can be transferred to the memory. Also, the data can be transferred from the memory from memory, right? Using the memory channel. So this is also hardware, right? So in the communication, so channel is the hardware resources, right? So in order to provide the high bandwidth from the memory, then we need to increase the channel width. Okay, so it means we need to increase the number of channels. What's the problem? Cost. Okay, uh, actually you need to so a computer system is hardware, so which means so you need to also understand the hardware cost, the hardware cost of the computer system. So this is the CPU, and then this is the RAM. And then I said that the DRAM is the external memory because actually DRAM cannot be fabricated in the CPU package. Okay, so so it's not easy recently. So but if you open the lid of 뚜껑 lid of your computer, then you can find the CPU chip, right? And then, so if you are using a desktop, then you can easily open the desktop case, and then you can find the CPU chip. But you can also find the memory slot. Okay, so different packages. So different packages means that so this is a single chip. A CPU is fabricated in a single package. It's a single chip, and then the RAM. This DRAM is is out of the CPU package. Okay, it's a different chip, different packages. So what does that mean? We need to connect the CPU and the RAM using wires. It's a PCB wires. Okay, it's a physical wires. Okay, it's a metal wire. It's expensive. It's very expensive actually. Okay, so in order to build a system like this, then actually we need to add the interface on the package. And this interface is called the pin, right? Because in order to transfer data from the one package to other packages, then this data need to be provide to the external interface. That this is called the pin or bow. Okay, so actually pin is also expensive. Okay, pin is expensive, and then the metal wire on the PCB is expensive. So what does that mean? In order to increase the bandwidth, it means the channel, it means the wire. Okay, in order to increase the number of channels between the CPU and external memory, like DRAM, the cost is very high, right? So that's why the external the memory bandwidth, this bandwidth is it's very precious resources. So it means we cannot increase the memory bandwidth infinitely. Okay, so it's very precious, and then it's very cost. The cost is very high. So what's the problem? We want build the system like this, but in order to build a system like this, then the cost is very high. So the cost is also very critical, right? But idea is that, oh, this memory is slow. This is fast. But we want to increase the performance. So in the real world, think about the real world. Uh, it's not good. But anyway, so think about it. So you want to hire workers, or you want to hire workers, right? But the performance of each worker is low. Then how can you increase the performance? We can increase the number of workers, right? Memory is slow, CPU is fast, but we we want to increase the bandwidth from memory. Then how can we increase the bandwidth, which means performance? We can increase the number of memory chunks. So you can find the bank here. It's called the bank. So bank is the bank represent the independent memory chunk. So this is the independent unit. So we can provide the request to the each bank, and then we can get data from the bank. But as you can see, the bus width is narrow. Then how can this work? Oh, each bank, each bank is slow, right? It means if the request is given to a certain bank, after a long time, we can get the result, the response from this bank. Idea is that, oh, we we give the first commands, first request to memory bank 0. Then we need to wait long time. But during this wait time, we can give the second request to the memory bank 1. And then while this memory bank 1 is working, then also we give the third request to the memory bank 2, another request to memory bank 3. Then it works like this. Okay. So this is request. And then after some time, delta t, we can get the response. So in this case, we give request to the bank 0, and then after some time, we give another request to the bank 1. Because the bank 0 will respond at this time, so this is the idle time. So during the idle time, we can give another request to different banks. Okay, the bank. You can give another request to the bank 2, and then another request to the bank 3. So, so by doing this, it is possible because the memory bank is slow, right? So there are long idle time in the if we just use one bank. So idea is that we can have multiple banks, then the request is given to the banks sequentially during the idle time. So what's the benefit? We can increase the bandwidth. We do not increase the bus width, right? But in order to reduce the idle time of the slow memory, we can include multiple memory chunks, and then each chunk is called a bank. And then the request is given to the different banks sequentially. So we can control the slow memory like this. Okay. So actually, this is very important mechanism, right? It's a kind of mechanism, right? So by doing this, we can handle the slow memory. And then also, you know, in the real world, so we can apply the similar mechanism, right? For the slow workers. So this is called the bank level parallelism or memory level parallelism. So it means we just utilize the multiple memory chunks to increase the performance of slow memory, right? So DRAM, DRAM is composed like this. Also the SRAMs like cache memories are also composed like this. So we can utilize the bank level parallelism or memory level parallelism to handle the slow memory. Okay, so this is very important concept. So I hope you can understand this one. Okay. Okay. So I'll stop here. Thank you for attention. See you in the next class. 감사합니다.